Hello, everyone. My name is Mehdi Hashimipur, and I'm a data scientist at the US Department of Transportation. I'm leading an ongoing project at the Bureau of Transportation Statistics, intending to build an internal commercial aviation flight database system. This presentation is about one of BTS efforts to achieve this goal by doing a proof of concept to automate the data ingestion and analysis of the FAA SWIM data using Microsoft Azure and Databricks. So I will give you an overview of the project, and then Marcelo and Sheila will discuss the infrastructure, architecture, and the data processing part respectively. So building the commercial flight database system helps BTS to measure and report aviation system performance. And some of the potential benefit of that is enabling timely estimate of enplanement and on-time performance, supporting special aviation studies, and providing a source of data to aviation dashboards and other statistical products. And finally, serving as the aviation component of the transportation disruption and disaster system. So most of these objectives could be achieved by using the FAA SWIM service as a major component of the commercial flight database system. Let's start with understanding what is the SWIM service. SWIM stands for System-Wide Information Management, which is the combination of multiple data services, including airport, flight, aeronautical, and weather data. SWIM is the digital data delivery platform that turns raw National Airspace System, or NAS, data into meaningful information for aviation stakeholders. Consumers can connect to the system with a single connection through a source FAA telecommunication system, where they can retrieve data coming in from producers in real time. So in order to develop the system for the proof of concept, we used one of the SWIM services called TFMS data. And TFMS, or Traffic Flow Management Service, also referred to as air traffic management, is the craft of managing the flow of air traffic in the national airspace system based on the capacity and demand. TFMS service provide aircraft situation display data, and also it include aircraft scheduling, routing, and positional information. So Terminal Data Distribution System, or STDS, is another SWIM service that convert legacy terminal data collected from airport towers and terminal radar approach control facilities into easily accessible information. So STDS stream gives user access to data from over 200 airports. And the stream data comes from over almost 400 individual systems into SWIM with XML format data. And the volume of data that we are receiving by turning on the SWIM stream is huge. For example, for 1 week worth of TFMS data, we collected over 15 million XML messages, which takes terabytes of space. And ingesting and processing these messages is challenging and require fast and reliable data processing workflow. Here in this slide is the architecture for different SWIM services, which consists of many services and data components that are getting streamed by various producers, where they are from FAA itself to other external publishers. And the main categories of data are including weather, flight, and flow, and many other aviation-related data components. So using the SWIM data, and more specifically the TFMS data, would help BTS to answer questions like airport airline performance, airport time delays, on-time performance estimate by cause, and so on. Also air cargo traffic, economic impact of flights delays, diversion and cancellation, such as financial impact of the flight delays and flight path analysis, operational and passenger impact of flight delays and cancellation, such as flight pattern interruption and late arriving flight patterns. And finally, the passenger impact of flight delays, diversion, and cancellation. So the initial conceptual architecture that we designed for your environment is consisting of getting connected to FAA SWIM service through either a virtual machine approach or an HD Insight approach by using Apache Kafka for streaming the raw XML messages, then processing these messages and storing them in a structure or semi-structure format into a data lake, making the data ready for further analysis. To implement this system architecture, Marcelo will discuss more about the development phases, system component, and its deployment in the DOT Microsoft Azure environment.
Thanks, Mehdi. So let's talk about the infrastructure. So the initial goals from the infrastructure point of view were clear since the beginning of the project. We wanted to help data scientists like Mehdi and Sheila getting access to a SWIM and internal on-prem data sources so they could do and start their work as soon as possible. Not to worry about building the required infrastructure, all the post-provisioning configuration tasks that come with it, like server configuration, Databricks resources, etc. Making sure it is secure and up to internal security standards. And of course, should be able to scale based on demand or type of workload. In summary, we had to automate as much as we could, and so they could have a working environment quickly and ready to be used. Based on these goals and the conceptual architecture showed by Mehdi before, we came up with this physical architecture, which from the infrastructure point of view gave us a pretty good idea of all the cloud resources and services that needed to be scripted and automated. A couple of things to notice here is that we are using the Solace source connector in Kafka in order to ingest the data. Solace provides source and sink connectors that you can build and easily deploy them in your Kafka cluster. And with some minor configurations, you are set to ingest basically any SWIM data source you want. And best of all, is open source. Second, we are using plain open source Apache Kafka, which makes this solution portable. If needed, you could easily deploy it somewhere else. We focus on automating these three categories. Infrastructure itself, which includes all the initial networking, subnets, security groups, VMs, Databricks workspaces, storage, everything. Second, Kafka. Now we are on the post-provisioning configurations, which includes Kafka installation, configuration, along with its software requirements like Java, for example. It also involves a SWIM required configuration to access specific data sources. Having the right configuration files in the right place. The Solace connector to ingest the data and its required dependencies and libraries. Finally, Databricks, which involves cluster creation and configuration, require libraries like Spark XML to parse and analyze the data, import initial notebooks, and setting up secrets to properly mount and access the data lake. At this point, we knew what we needed to build and what we wanted to automate. Now we had to come up with the right tools. We started with Terraform for obvious reasons. So far, it's the best tool to have infrastructure as code, especially if you are in a multi-cloud environment. This thanks to its great number of providers and common language across all of them. Has support for all the resources we wanted to build, allow us to reuse code using modules, customize it using variables like VM sizes, for example, that might change based on the environment and type of workload. Maybe production is going to require a beefy machine, whereas development is just a small test and a small VM. We can also review the changes before they are applied, which is great. And Terraform Cloud, which allow us to store the state of this infrastructure so we can have a distributed team, not just one person clicking through the portal. Once the environment was ready, the next step was to do all the post-provisioning configurations. For that, we wanted to provide options. So we created Chef Cookbooks and Ansible roles. Both provide the same functionality we needed. By building these configurations as code, it also works as documentation on how these services were configured in order to access a SWIM under data sources. This in case we wanted to access different SWIM data sources than the initial ones we are using. So we will be able to scale. We avoid configuration drift, which is a very common problem when you have multiple environments. In summary, we have consistency across all our resources and environments, which is a huge win. Basically, no more snowflakes. For Databricks specific configurations, we use Databricks CLI. It is still experimental, but it provided everything that we needed, like import initial notebooks, create clusters using JSON templates, install libraries like Spark XML, and much more. Again, still under development, but very powerful. Highly recommended if you want to interact with your Databricks environment using CLI and not the UI, which is perfect for automation. So since we are having everything as code, it just makes sense to store it in GitHub and use GitHub Actions to orchestrate it. GitHub Actions allow us to create workflow automations for any OS, any language, and any cloud. It even comes with some predefined actions that you can use as a starter point. Again, highly recommend if you want to orchestrate these automation pipelines without much effort. So putting it all together, we have this flow where everything starts with the developers pushing code to GitHub, submitting pull requests, PRs, so their changes can be reviewed and approved. Behind the scenes, GitHub Actions workflows get triggered, which result in changes either the infrastructure, Kafka, or Databricks configurations, you name it. Finally, here are some things that we learn along the way. The initial setup might take some good time. Having your tools like Terraform, Chef, Ansible, GitHub, all of those properly configured with proper permissions and access takes some time. You need to have some sort of service account with the right permissions to create, modify, or delete cloud resources. There is also some learning curve, especially if you are not used to having infrastructure and configuration as code, and the GitHub flow. Having branches, submit PRs to review code before it's applied, and things like that. There was a lot of test and fail at the beginning, mostly because of security, since all the traffic had to be internal, and some endpoints were not open or needed to be open. And those changes also take some time. But at the end, everything worked out just fine. Now we can deploy this solution easily with minimal effort in multiple environments if it's required or needed. Finally, all this code is open source and can be found here. Please feel free to use it and extend it. And now for the best part of the presentation, Sheila is going to show us a cool demo of the end result. Thank you.
Thank you, Marcelo. What I'm going to show you now is what we did with the TFMS data and how we processed with it. So what you see here is our idea of what the future state architecture would be. And what that would be is to include either relational databases, so something like Oracle and Sybase, which have historical data in it, and couple that with the streaming data and bring that into a raw Delta Bronze table using Spark and Databricks runtime. And then from there, batch processing to parse the XML data and do schema validation against the very complex nested TFMS schemas, and then do joins and aggregations from there to be able to really get power out of your data and be able to perform your analytics or predictive analytics, machine learning processes on top of that. One thing to note in the demonstration that I'm about to show you is that we look specifically at the TFMS data stream. The future state, however, includes the other data streams coming in from SWIM data. And another thing to note is that the environment that I'm going to show you is a mirror of what was implemented at BTS. What you're looking at now is the Databricks platform. The architecture from the slide that I just showed, we've implemented in a series of 3 notebooks within Databricks. So this is a simplified diagram of what we're seeing. Again, we've mirrored the BTS environment by hooking up from Kafka to the SWIM data using the Solace connector that Marcelo talked about. From there, we consume the messages into Databricks and immediately stream out to a bronze Delta level table. That's the raw XML streams. From there, we in a batch processing mode where we specify a time period, we bring in those XML messages from the bronze table and we parse it using the Spark XML package and write that out to our silver level Delta tables. From there, we can choose the time period, bring in the data from the silver level tables during that period, and do joins and aggregations of the different message types to be able to start looking and doing our data exploration analytics against the data. We're going to focus on this last line right here where we're going from silver to gold. But one thing I do want to point out before I jump right into there is show you what the bronze level XML messages look like. And you'll see that right here, that the XML messages are really hard to just look at and understand what's going on in them. So the next step was to parse it using the Spark XML package. If we scroll down, we can see what that would look like for the messages themselves, that we're able to flatten them into a nice looking data frame where we can easily see different data within the data frame itself. Now we're going to jump right into the gold level tables so we can see what the data looks like and understand these TFMS messages. One thing to note here is that there are 20 different message types coming into TFMS. And we are consuming them all and writing them to the silver level tables. So what we're going to do is take that silver level data and enrich it with reference data. This is publicly available reference data on, dealing with what the airport codes are, what cities they're located in, as well as the airline information, what the codes are compared to the airlines. Now, if we scroll down, we can see that we're going to focus on departure, arrival, as well as flight plan creation information and bring all of that data together. We can see we have about 30,000 messages and departures and 30,000 arrivals, as well as about 11,000 flight plan creation messages. So what we're going to do is look where we have information for all of them so we can start understanding the delays. So how the scheduled departure and arrivals compare to the actual arrival and departures. We can see here the flight plan tables, so you can easily see that we have all of the information available to us. Now, when we join this information together with flight plan with the actual arrivals and departures, we can calculate delays on arrivals and departures. And when we start looking at it and visualizing that data, we can start understanding where there are larger delays in arrival and where are we landing early. So you can see that between San Juan and Memphis, there were larger, on average, arrival delays during the 4 days of data that are taken. This data was taken between May 25th and May 28th, not inclusive of 24 hours. Within the BTS environment, this data is running 24 hours a day, 7 days a week. So they are consuming all of the data on terabyte or petabyte scale, and these same notebooks are running there. So these are actually consuming a very large scale of data. For the sake of this demonstration, I'm showing a small portion of it. Again, we can start even doing more analytics by calculating distance between airports and start looking at what about the elapsed flight time compared to what the flight plan said the elapsed flight time should be, and start getting metrics as to where are we overcompensating for the flight plan, and where are we not giving enough time for that flight to happen. And so we can begin to start kind of correlating these to potentially weather patterns or wind patterns. And if we keep going, we can pivot and start looking at cancellation messages, because within the TFMS data, there are 20 different message types. So we have a lot of data at our fingertips. So in this case, we have 1,265 recorded cancellations of flights within those 4 days, and those hours that we have data for those 4 days in this case. If we enrich it with that flight, with the airline and flight and airport information, we can get a little bit of we start diving into the data and understanding that American Airlines seem to have canceled the most flights during those 4 days. We can also do analytics and see what routes were canceled the most. In this case, Albuquerque to Phoenix was canceled 56 times during that time, during those 4 days. So maybe we start looking at weather patterns, and maybe there were big storms in that area. So it's something that we can start diving into and analyzing why these cancellations are occurring. At the same time, by looking at American Airlines, we can start doing some sort of analysis on where are these cancellations occurring. So these are different departure airports from American Airlines flights. We can see that from Miami, most flights were canceled. Well, Miami is an American Airlines hub, so that's not necessarily too surprising, but where are these flights going that they are being canceled? So if we look into what's landing in Miami or what's departing from Miami, we can see that the flights going to Havana, Cuba, that 8 were canceled during that time. So from this, we can see that by using Spark XML to take these XML messages and flatten them out, we can really start diving into the root cause of why different delays and cancellations are happening, bringing in different streams of data. We can start to do predictive analytics. We can look at seasonal flights and see how the seasonal flights are changing in terms of cancellations in different areas of the US. And we can start diving in more. Thank you.
So we learned a lot of lessons along the way with implementing the data processing and looking at the XML messages coming in. The first is the Spark XML package is very powerful and that it's improving. And actually, doing this project with BTS, we were able to actually improve that Spark XML package to deal with these very complex and nested schemas. And currently, we're still looking into ways that we can improve it even more. So this is a constantly evolving package that's becoming more and more usable. Next is to do the schema validation. We actually ran into every XML message that we were loading up the different schema files to, and the nested schema, we're bringing it in from storage, opening them, and then validating our data against it. So what we did to mitigate any file IO latency was actually take that schema and copy it out to each of the executors within the cluster. And what that allowed us to do is have that schema in cache, in memory cache, so that way we could easily and very quickly validate against the schema. So we went from validating on the order of minutes to actually validating in just seconds. The last thing we learned is that with the XML messages coming in, that if we infer that complex schema off of those messages as they come in, well, not all messages are as complex as they can be. And so if you're inferring against a small set of those messages, could be that when a very complicated message comes in, you could get a schema mismatch and have issues with that. So what we found is, based on requirements, that we could batch process on the order of an hour and be able to account for all of those complexities within the schema itself of these XML messages. So where are we going from here? Well, the first thing we'd like to do is take that data that we went through and processed and validate it against the data that's being provided by the airlines. So when the airlines give the data to BTS, they're able to look at it, and we can look at it against the SWIM data to see if the same information is available through these SWIM data messages. Also, we'd like to take a deeper dive into actually advanced analytics and look at predictive modeling, understanding the seasonal issues and flight delays and how that's going to affect passengers. Many of the use cases that Mehdi alluded to earlier in this presentation. And lastly, we'd like to open up this pipeline and allow more SWIM data feeds. So not just TFMS, open it up to STDDS and the other streams coming in that we saw on the earlier slides. So lastly, I would like to say that if you'd like to contact us and learn any more about the project or talk with us more, our contact information is here and available for you. And very lastly, I'd like to thank the U.S. Department of Transportation, as well as the Bureau of Transportation Statistics, and especially Mehdi for allowing us to collaborate with him on this work. Thank you.